In section 110, we're going to be modeling data with linear regression equations. Regression is going to be a big deal for us throughout this whole semester. This is our first introduction to it, but I did want to emphasize that we're going to get really good at it as we continue on through the rest of the chapters here, and this is just our first chance to really introduce and get some practice with this. All right. Our first objective is to recognize when patterns of points in a scattergram have a linear form. Recognize when the pattern in the scattergram shows that two variables are either positively or negatively related. So again, thinking about linear, positively or negatively related. Estimate and draw a line of best fit through the points of a scattergram. Use the graphing calculator, and we're using Desmos for this, to determine the equation of the line of best fit. This is also called the regression line. That's what we're talking about when we talk about regression, is the line of best fit. We're going to measure the strength of the correlation, right? The correlation coefficient. And we're going to recognize that a strong correlation does not necessarily imply a cause or effect relationship. All right. So first, we've got a situation up here where there's a data set, and these are the costs for private, nonprofit, four-year colleges and years since 1981. So in this table, they have already calculated the number of years since 1981. Sometimes this middle row is left for us to do. If our years are 1981, 1991, 2001, 2011, 2017, and I wanted to talk in years since 1981, I'm sorry, since 1980, looking down here, 1980, we are 1 year since 1980 in that first year. Then we are 11 years since 1980, 1991, and so on. We can subtract 2017 minus 1980 to get 37. We would be able to compute each of those values, but they've been done for us here. The first thing we want to do is draw our scattergram. When we make a scattergram, we don't need to make it on paper right here. We're going to make it in Desmos, and I've actually already went ahead and typed in my values into my Desmos graph. I haven't zoomed yet, so I'm going to zoom fit on those and see that data plot. All right, so I can see what my scattergram looks like. You can imagine I would draw it here. It looks like this, noticing that the scaling on the x-axis seems to be by 5, 10, 15, 20, and the scaling on the y-axis seems to be by 5,000, 10,000, 15,000, 20,000. So a very vast difference in scaling on the x and y axis, counting by 5 or counting by 5,000. All right. Question 2 asks us, does there appear to be a linear relationship between the year since 1981 and the cost of tuition? So does this appear to be linear? Again, I have my scattergram still up on screen here because the appearance of linear is evident in the fact that I do seem to have a constant rate of change. I can imagine drawing a straight line through these dots. So that's going to be why I answer yes. Yes, a straight line is going to fit those dots well. They look like a linear pattern. They have a constant rate of change. They look like a straight line would connect them well. So we're going to make ourselves that note down here. Yes, because there is a constant, that's what we know, constant rate of change. As the years increase, what is the general trend in tuition costs? So as our years increase, what's happening to tuition costs? And we saw our dots increasing as well. So as years increased, as we go sideways, we also go up. So tuition increases as years increase. So as the years increase, the tuition increases. That was our pattern that we have observed. Okay, so now it's asking us to visualize what this line would look like. Again, my sketch is really rough here, but I could visualize what this line would look like. And we're going to next find the regression line. The regression line is going to be the exact line, and we need technology to assist us with this. All right, now I'm going to insert some additional directions over here. They do show us the calculator directions for those old handheld TI calculators, but we're going to do this differently on Desmos. I'll show you first, then I'll write it back over here in my book. Let me get my Desmos tab. All right, so I'm going to make this just a teeny bit bigger. I'm going to talk about how to remember how to do this, and then I will write down the formula for this for you. But I want to make a line, and I know that a line is of the form y equals mx plus b. So I'm just going to write that first. Knowing what a line looks like helps me with the form for this, y equals mx plus b. Now, I need to tell Desmos how to make this line. And I want it to approximate the line that's going to best fit this data. So the first thing I'm going to do is take off the equals and make it an approximate sign with a tilde. It's next to the number 1 key on my keyboard. So I'm going to use the approximate symbol to tell it to create the best line it can. And then I'm going to tell it where to find the information. So X, I want it to tell it where to find the X data. That's from the list that in this table is called X1. So I'm going to change the name of this from X to X1. And then where to find the Y data? Well, that's in the list right here called Y1. And there it is. Okay, so the regression line statement is Y1 tilde for approximate. Y1 is approximately equal to mx1 plus b. And what this does is it computes the slope, the m value, as you can see in our parameter section, and the y-intercept, the b value, that will best fit this data set. So I'm going to rewrite this as a function now. My function is going to be f of x equals, now I know the m value is 631.776. X plus the b value is 9,871.73. Let me expand this just a touch so I can see that full line right there. Now, I am going to notice a couple of things about this. One of them is the lines are graphing on the same spot right here. Now, if I zoom in enough, they could be slightly off. Oh, I'm not going to be able to see it by zooming in. They look really dead on right here. But what I was thinking was that there is a possibility that these values have more than 3 places, so I might see a slight variation, especially if I didn't write down all 3 places. If I only wrote down one place, for example, I would be able to see more of a difference between them potentially if I were to zoom in again on them and put those 3 places back. Okay. What I would also like to note about those parameters, though, is this has actually assigned the letter m with the slope value. So if I just type the letter m, I actually get the full value for that slope. So if I did need more decimal places than the 3 that I can see up here, I could hit the m key and I could get more places because the letter m has been assigned with that slope. The same thing is true of b. The letter b has been assigned with that value. So one more option is I could have written my function as f of x equals m, because m is assigned with that value, x plus b, because b is assigned with that value. I like to write it in terms of these numbers, though, so I can see the numbers even if they've been rounded. But if I did need a little more accuracy, you can see that graphing it with just m and b will give the accuracy that we need there. Okay, let me zoom. There we go, back out. Okay, so I'm going to write in my book for a moment. Let me just pull this off to the side. And the process that we need to do a linear regression is to type y1 is approximately mx1 plus b, where x1 and y1 are the labels from the table. So these two things are going to match the table x1, y1. So just as a note, if you had been doing more than one table and this was x2, y2, well, then you would want this to be y2 and x2 so that they match whatever you had your table called. You could rename your table T and N, and so if that was the case, then you would want N and T. Whatever you have them called in your table is what they need to be called in the regression statement. Okay. Now, we're going to do some more work with this. So we're going to write the result. Oh, I got to look at my decimals equation right here to write the result. And 2 places it says, so we can round ours. We had 3. We're going to write it down now with 2. So the equation is going to be I'm going to call it f of t here because the inputs were years, and it does say let t be the number of years since 1980. So f of t is going to equal 631.78, if I round that up correctly, t plus 9,871, oops, I missed the digit there, 0.73. All right, let me move that decimals back out of the way. Now, I'm bringing my decimals back here in just a second. We want to fill in the actual, we have the actual output from the table, from the initial table. We want to fill in the model's predicted output. So this is the line of best fit, the line that would best fit these data points. But I should have emphasized the fact that it's not perfect. There are some points that are just above or just below the model, and that's perfectly fine. There was nothing more perfect that I could have got, though. So this is the best fit that was possible using a linear function. But there will be some error in the predictions compared to the actual data. So that's what we want to look at next, is what are the predictions? I'm going to get rid of these lines so I can see my function up here. I'm going to make myself a new table, and I want to fill this into my function f of x. So I'm going to do an autofill table, f of, and the inputs for the second table are x2s. And now I'm going to type in my inputs and have it autofill are 1, 11, and up through 37. All right, so I'm going to slide this over to the side here, and we're going to write those in for the model's predicted outputs. Year 1, it was 10,503.5. I'm just going to keep one place right here because we're comparing them to a whole numbered value. Then I have 16,821.3, 23,139.0, 29,456.8, and 33,247.4. All right, so I wanted to compare these to the actual output. All right, so we're pretty close. We couldn't really see it on the graph how far away we were going to be. We're 23 or so off. Here we are off by a couple hundred. Here we are off by almost 1,000. That was one of the ones that we could maybe see had a slightly larger discrepancy. This third one, you can actually see the dots being in different places. You can see it here too, where they're off by 100, but the ones where they were off by under 100 seem really close. There's a little bit of a difference here. I can see the green dot. This one I expect to be really close because I don't see that green dot at all. Let's see how close those are. So these ones are off by, well, it looks like it's close to 100, so yeah, but a little bit less. And then this one right here, maybe a little bit more. We're off by a couple hundred here. So there is some error, but our predictions will ballpark the actual output. What we're hoping is that they're also going to ballpark predictions for years not in the table so that we can get an estimate. There's going to be error, but that our estimate will get us around the right figure. None of these are 10,000 off. They're maybe a couple $100 off, but they are going to get you in the ballpark. If you're thinking about your tuition being $33,000, whether it's $33,200 or $30,400, it's a $33,000 part. That's the important part, trying to figure out if you're going to be able to afford the tuition. Believe it or not, the $200 is relatively small in comparison to the actual values. So we want to get a ballpark prediction for next, the year 2004. And because this is since 1980, if we compute the difference, 2004 minus 1980, that should give us a difference of 24. And so we're going to be using an input value of 24. All right, so back over to the decimals so we can get this plugged in. I can do it in the table since I have an autofill table right here, but I'm just going to do it underneath in function notation to keep this question separate here. I want to plug 24 into the equation. So f of 24 is $25,034.35. All right, so again, this may not be the actual answer, but it is our predicted answer. We're somewhere around the $25,000 would be the tuition for the year 2004. We don't know data from the year 2004. It was not in the original table. We had 2001, we had 2011. So this is our best guess prediction of what that tuition would have been. Okay, now we're going to talk some more about making those predictions. There are two kinds of predictions we can make. If we make a prediction that is within the boundaries of the data set, it's called an interpolation prediction. And if we make a prediction that is outside the boundaries of the data set, it's called an extrapolation prediction. This is important to note because interpolation predictions are more reliable than extrapolation predictions. So I'm going to look at my data set again and show you what I'm talking about. In this data set, let me zoom back over on it. Interpolation predictions are predictions for values that fall between the first and the last data point. These are more reliable because these values, the 1 through 37, are the values that were used to compute the model. Each of these ordered pairs was used with the regression process to compute the model. So anything beyond those was not part of the computation. So these are guesses that go beyond the boundaries of the data set. The closer you are, the more reliable the predictions are going to be. So there's also a difference between near extrapolation and far extrapolation. But far extrapolation, they're no longer reliable predictions. We can no longer say with any certainty that 150 years later, the tuition rates are going to follow the same formula that they did in this tighter area between 1 year after and 37 years after. Okay, so it's important to note when you're making a prediction, whether you're making an interpolation or an extrapolation prediction, because that gives some commentary on whether or not the prediction is reliable and how reliable it might be. Okay, so moving back to part B here, use the regression equation to predict the average tuition for years in 2020 and 2025. So first of all, I need to figure out what my input value is going to be for these. So for 2020, if I subtract 1980, that would be an input of 40. And if I take 2025 and I subtract 1980, that would be an input of, oops, I meant to say 45. I don't know why I was writing 40 again. 45, messy 45 there. So what I need to do is predict f of 40 and predict f of 45. Okay, so we're going to make those two predictions here. Let me scroll down. We'll do f of 40 and f of 45. F of 40, we have a prediction of tuition in 2020 costing $35,142.77. And then for 2025, F of 45 gives us the prediction that tuition costs $38,301.65. Which prediction do you believe would be more accurate? Okay, so again, we are thinking about the 2020 prediction with that 40 as being a near extrapolation, and the further away we get, even just to get to 45, the further away we get from the model, the less accurate that is going to be. So always the nearer extrapolation is more reliable than the farther extrapolation, and because the 40 input is closer to the data set, that's going to be our more reliable prediction. So 2020, because it's closer to the edge of the data set. And another way to say that is that it is a near extrapolation as opposed to a far extrapolation. I'm running out of room, so I'm writing a little small here. Near extrapolation. There we go. All right. And last part D, use the regression equation to estimate the year in which the average tuition room and board will be at least $45,000. All right. Previously, when we were doing the predictions for 6A and 6B, it was in this year what was the tuition. So they were giving us input values. If they were giving us input values, I could put them into the function. This is an output value. This is not an input value, right? So if that's an output value, then I cannot put it into the function, but I can make a prediction because output values are y values. I can graph y equals 45,000, and then I can look for where that crosses my model. So let's do that. We have our output y equals 45,000. We can see now the height of 45,000. And I can say that makes intersection at the input of 55.6. So I'm going to make a note of, I'm going to draw the picture real quick. We have our lines and they're crossing at 55.6, comma 45,000. And this was the line y equals 45,000. And this was our regression line, or f of x. Sorry, I was labeling those things at the bottom. If I can slide my book up a tiny bit, you can see my labels there. All right. So this means that 55 is the year. So 55.6 years after my starting year, which was 1980. That's going to put us midway through 2035, or we can round that up to 2036. So we would predict that in 2036, that would be the year that tuition is at least 45,000. Okay. Back to predictions for just a second. Again, we made our input predictions and our output predictions differently because inputs go inside the function. I also could, I'm going to turn this line off for a moment so we are looking back at the 45. I could have made this prediction graphically instead of with function notation by recognizing that that input of 45 was an x value. And if I graph x equals 45 and find out where that hits my graph, it does hit at the same value that we see here, the 38,301.65. So it is possible to do those predictions graphically by recognizing that you have an x value, so x equals 45. Most of the time, I find it more convenient to call the function with function notation, but either way that you choose to do this would be just fine. So I'm going to hide that one again. When I have a y value or an output value, I don't have a choice. If I want to do this on decimals, I don't have a choice for how to do it because I cannot put that into my function. It's an output value. So I can find it graphically by finding out where that line crosses the graph. We also could just click and drag and try to find 45,000 as an output, but that's much less efficient than it is to graph the 45,000 and click on the intersection. That took a lot more, and I didn't even find it. So clicking on it is so much easier to get to the correct input value. Okay. All right, so we have another situation here. So I'm going to need to get a new decimals graph going. We are looking at bachelor's degrees projected to be earned by women, and we're looking at years since 2019. So 2019 is their year 0, then 2020 is year 2. They've already done this part for us. They will stop doing that relatively soon, and we will have to make sure we always are looking at years since. So we do not put in the top full year values ever. We only use the year since. We're going to input those bottom 2 rows into the columns for our decimals graph. So I'm going to keep this open. I'm just going to do a new tab for a new decimals graph, just in case we come back to the other question. Sometimes we do that. All right, so we're going to insert a new table. We're going to have 0, 2, 4, 6, 8, and just got to type in my outputs. Okay, so got those entered and going to zoom over to the data set. So first job is sketch the scatter plot. And then we want to visually confirm that the scatter plot appears to be linear so that we know that it would be appropriate to make a linear model. So you can see that and think to yourself, a straight line would marvelously fit that data set. It looks like a pretty straight pattern. Okay, so get the regression equation for part B. So I know this table is called x1, y1. So I'm going to start with y1, approximately mx1 plus b. And there we have it. So I will pinch this up so I can write down my model here. My model is going to be f of t. Again, the independent variable, we're going to call it t here as directed in the table. And I need to look for the m value, that m parameter. So it is 16.15 times t, m times the independent variable, my mouse out of the way, plus b, which is 1082.4. So I am using Desmos to come up with the equation that best fits this data. What it does behind the scenes when you do that regression line is it takes all of those ordered pairs and it tries to calculate the average slope between any two pairs of ordered pairs. And that's a lot of computations because it's got to think about the first and the second, the first and the third, the first and the fourth, the first and the sixth, and the second and the third, second and the fourth. A lot of computations right there to try to find the perfect slope that would best fit all of the ordered pairs looking together. So it does it really quick, and it's amazing that it can do this for us. What is the slope of the line? What is its practical meaning? Well, I know the slope. It's right here at 16.15. That's the easy part because it's told to us. The interpretation part, that's where our brains have to fire in and figure out what this slope means. So I'm going to hide Desmos so that I can see the table on my screen here. There we go. Sorry about the flickering. I need to know what output is. So the output, which is the number of bachelor degrees earned by women. Or is this by women? Yeah, I think so. I'll just write number of bachelor's degrees since it's mentioned down here, or it is stated up here. The number of bachelor's degrees earned by women is now, what's it doing? Increasing or decreasing? Positive number means increasing. By how much? That's my slope value. By 16.15 units. 1,000 degrees is the units on this one. This is the number of degrees, 1,000 degrees per how often? Year. So per year. So I have to have all of those words really to get the practical meaning for this. What is the output? What is it doing? How often? And my units on both input and output. Okay, and then I get to use the regression model to predict the number of bachelor's degrees that will be granted in the year 2030. Okay, so 2030, that's going to give me an input value, but my years we're counting since 2019. So the first thing I need to know is how many years have gone in between 2030 and 2019. So I can figure that out. 2030 minus 2019 is 11. So 11 is going to be the input. So I need to do f of 11. I haven't typed the function yet, so I actually have to do that part first. F of t equals 16.15 t plus the 1082.4. I have to enter the function so that it's in function notation. Prior to that, it was just the regression statement, which helps me determine what the parameters were. but I hadn't typed the function in a way that I could evaluate it. Now that I have, I can enter the f of 11, and we will see that our prediction is 1260.05. Now, we should always answer these things in a sentence. So instead of just the number, we'll jot a quick sentence here that the model predicts that there will be 12,060. I can drop off the 0.5, just I can run it to one place, or just draw the nearest whole for the number of degrees. Degrees earned by women. I missed units. This is not just 1,260 degrees. This is 100. This is 1,000. 1,260,000, which actually would convert to 1,260,000 degrees earned by women. I was thinking to myself, like, that's too few degrees. I was wondering if it was like just at one particular university until I remembered that it was in thousands. So this is supposed to be in the United States. If I look back up at the top, number of degrees earned in the United States. So that 1,000 really needs to be in there to make this make sense. In 2030, we're predicting that 1,260,000 bachelor's degrees will be earned by women. Okay, now the latter part here, we want to talk next about the correlation coefficient. The correlation coefficient R tells us how good our model is. I'm going to look back over at our decimals graph here for a minute to show you where you see R. R is in the statistics area of the regression. You can actually see R squared and you can see R. Both of those, R squared really just literally is the value of R squared. Sometimes in stats, we would use R squared instead of R. For right now, we're referring to regular R. When we get into some of our other model types, like our quadratic regression or our exponential regression, R squared will eventually be the one that we will be looking at. But right now, we can actually look at R or use them interchangeably. They're both very close, 0.9915 or 0.9958. This R value, think about it as a percentage. It's showing you how close your value is to being perfect. As a percentage, 1 would be perfectly 100% accurate. So the closer you are to 1, the better your model is. So 0.9958 is very close to 1, which means this is a very good fit to the data. Looking back at our previous example, we see a 0.9988. So again, this one is a very good fit to the data with a very high R value, a very high coefficient of correlation or correlation coefficient. You can phrase that either way. Okay, so back to our book page here. Looking at the R value specifically, the R value can be positive or negative. If the R value is a positive number, it means that your correlation is increasing if R is greater than 0, and your correlation is decreasing if R is less than 0. So R's was increasing in both cases, so we had positive R values. R squared is always positive, of course, but R itself can be positive or negative depending on if the model increases or decreases. So we got a couple of examples here. In the first one with an R value of -1, that is a perfect negative correlation. It would line up exactly as a line. And if I skip over to the last one with an R value of +1, it would be a perfect positive correlation, exactly a line. This thing in the middle, there is no linear pattern here. This one has no correlation, and that's because the R value is so small. It's almost 0, not almost 1, 0.06. No correlation in that case. It's scattered. It's not a line linear pattern. We can see a few more graphs down here helping us to look at R's that are not perfect or resulting in no correlation and see what our conclusions are for these. So this one is a strong negative correlation. The negative just implies that it's decreasing. That's decreasing. And it's strong because we're close to negative 1, 0.99. This one's going to have a moderate negative correlation. As you can see, the strong correlation, it's tighter in the shape of a line. Moderate's a little bit more scattered. And this one has an R value of 0.89. So the moderates are going to be R values that are in the 0.7s or the 0.8s. So anything where your R is, let's say, 0.7 to 0.89 would probably be in the moderate. And I would probably say if you got into the 0.9s, you would get into the stronger area. So something in the 7s and 8s is going to get you in the moderate area. If you get a little bit less than that, you're in the weak correlation. So this one's weak. It's not no correlation. It's weak because there is still this general decreasing trend to it, but it's not as tight as it was in the other cases. But it does have that thicker downward negative correlation. So something in the 0.6 or the 0.5 is probably going to be weak, maybe even into the 0.4. We're going to be in the weak correlation area. Okay. The bottom graphs, we're looking at some of the correlations that are positive, but again, you'll see that you have strong when you have the 0.9s, you see the strong correlation tight towards that line. Here's another example of the moderate where you have a little bit more spread, and then the weak where that spread is even wider, but you do see that generally a very thick pattern up here, they are going up. So it's not the no correlation that we see above, where there's stuff up and stuff down everywhere. There's nothing to trend to a pattern in that one. There is a pattern in this bottom one for this weak correlation, something in the 0.5, maybe 0.4. You need to be able to visually see a trend. Okay. Almost done. We've got a few more. Looking at this one, we want to be able to predict which graph is which. For each of these, we want to match the correlation coefficient R with the corresponding data plot. So I've got one that is 0.84, one that is 0.53, one that is negative 0.45. So this would be a moderate correlation. These two would be weaker correlations. Two of them are in the positive direction, one of them is in the negative direction. So the negative direction right here has certainly got to be part C, that weaker negative correlation. And out of these two, I can tell that the second one, I guess the third one, but the second positive correlation, this one is more moderate. It's tighter together. So this is going to be our A, and then this weaker, more spread graph is going to be our B. Okay, so again, a correlation value of 0.85 suggests a moderately strong correlation. However, as we're going to demonstrate in number 9, it still might not be the best representation. So I'm going to take the moment to pause and type in this data, and then I will share this when I resume. All right, I've got my data table entered here. I'm going to zoom fit on that data and misclick. There we go. You can see the data set here. And then we're asked to determine the regression equation and correlation coefficient. So I'm going to write that in here. My table was x1, y1. So y1 approximately mx1 plus b. Okay, so this is an instance where the R value is 0.83, which indicates a moderately strong correlation. However, if I turn this off for a moment, I'm going to see that this pattern, although the data is relatively tight together, it's sort of like a swoosh mark or a check mark rather than a straight line. So even though my linear model seems to fit moderately well, that does not mean that linear model is going to be the correct choice of graph for this. So we have to look at both what our eyes tell us visually would be a good fit and the correlation coefficient tells us whether or not we've achieved a good fit. Together, those two things can help us define if a model is going to be the best fit for this data. So in this case, for this one, hold on, I need to move my Desmos graph off to the side so I can still see the equation. So the regression equation for this one would be y equals 0.516 x plus 1.572 with an r value of about 0.832. And do we think that a different graph might have done a better pattern? Yes, because that data set is that swoosh type. So yes, so the data does not appear linear. It appears to have some curve to it. So there is a curve that we can observe. Now, we're not in a position yet. Sorry for too low there in the page. It does not appear linear. There is a curve. We're not in a position yet to figure out what model would be better. But as we get more model types, we might be able to discuss what type of model that swoosh type curve would be. So that'll come in a later chapter. Right now, we can recognize that perhaps linear is not the best possible fit for this data. This equation is the best linear model possible, but that does not mean that linear itself is the best choice. That's what we're trying to emphasize. Okay. Last one, cause and effect relationships. A strong correlation between two variables does not necessarily mean a cause and effect relationship exists between the two variables. For example, there's a strong correlation between height and weight. However, an increase in height does not necessarily cause an increase in weight. Many other variables could cause an increase in weight, such as gender, age, or body type, and such variables often are called lurking variables that are hidden in the background and not named explicitly. So in this situation, suppose our home is heated with natural gas. There's a strong positive correlation between the amount of natural gas usage and the temperature outside. It's just a cause and effect relationship between these two variables. So does the temperature cause the natural gas usage? Possibly. There could be some lurking variables. So potential lurking variables. So if you're thinking that the temperature causes the amount of gas you use, possibly. If you're thinking about running your heater on natural gas, but lurking variables, there are other uses for natural gas, right? What if you are cooking with gas, right? If you're cooking with gas, then that's irrelevant to the temperature. When you're cooking, you might have a dinner party in the summer where you're going to use more gas, or maybe in the fall, or cooking could certainly cooking with gas could certainly be an outside influence to the number of gas. Or what if, like, I have gas for heat, but I also have a fireplace, and so I might not use as much gas in the winter if I'm burning a fire than I might if I was not. So there could be some variability in that. So other sources of heat could also be a factor. And I'm sure you can think of some others, just a few for examples, where there might not be a relationship. In order to infer a relationship between those two things, then the gas has to only be used to control temperature. If the gas is only used to control temperature, I only measure the amount of gas used to control temperature, then I can make the correlation. But if that gas is being used for other things, or there are other things used to control temperature, then the relationship gets murky. Okay, so in the last situation, in 2002, there was a publication that claimed the correlation between the people with two cars and a longer lifespan. Okay, so is there a cause and relationship between the number of cars you own and the length of your life? Interesting. So this is another situation where there are some lurking variables here. So the number of cars increasing seemed to indicate that you had an increasing lifespan. However, number of cars is actually probably a better indicator of income, higher income, and the higher income was probably due to it's not the income itself, but it's the health insurance or the access to healthcare that's actually maybe a factor right here. So access to healthcare. So even if there seemed to be a relationship between those two variables, that does not mean that the number of cars will cause the length of the life. There's some sort of maybe indirect relationship between the number of cars all the way up through maybe how that could affect your um, life length. There's another funny one you could search for and find this article on the internet, but there's a relationship between the number of pirates and the temperature of the sea. And as the number of pirates has decreased, the temperature of the sea has increased. And again, that is true mathematically because there were more pirates present earlier in history and there are fewer present now, and the temperatures of the seas have risen. But that is not a cause and effect relationship. It just is coincidental based on a timeline indicator where there is some hidden variables where both things were corresponding with time but not corresponding with each other.